Hello, my name is Adina. I'm from the Jülich Research Center in Germany, and I'm here today to talk about the tool DataLad. In particular, my talk is titled Data Management for Neuroimaging with DataLad. And talking about data management, that doesn't particularly spark joy. It is not exactly the most exciting topic there is, right? So I wanted to spice up my talk by starting with some what I would call scientific nightmares that you might personally know or fear. So consider you are a grad student and you write a paper, but it's close to the deadline, so you stay up late to generate good-looking figures. But you have to tweak many parameters in the process and display options, there's a GUI involved. And the next morning, you have no idea which parameters produced which figures and which of the figures actually fit to what you report in the paper. This is also very scary. Let's say your research project produces phenomenal results, but your laptop, the only place that stores the source code for the results, is stolen or breaks. And here's an example that sadly illustrates that from the real life, where a fifth-year chemistry PhD student looks for the thief of their laptop and offers them $1,000 to return just the data in their thesis folder in exchange, which is very bad. A graduate student, as an alternative scenario that might speak to you if you are, let's say, a PI, complains that a research idea does not work, but their supervisor can't figure out what the student did, or how they did it, or where it went wrong, and the student can't sufficiently explain their approach, which data are involved, which algorithms they use, which software has been a part of the picture. And what results from this are weeks of discussion and miscommunication that just hinder the progress of the project because the supervisor simply can't firsthand explore or use the student's project. And if you're a postdoc, this one might ring a bell. Let's say you wrote a script during your PhD, and that script applied a specific method to a data set. But now with new data and a new project, you try to reuse the script, but you somehow forgot how it worked, and it takes ages to get it to run. And then the final scenario, the final nightmare, is you try to recreate results from another lab's published paper. You base a re-implementation on everything that they report in the paper, but the results that you obtain look nowhere like the original. So if that sounded familiar to you, you're definitely not alone. And you also haven't been alone for the past decades, because these problems, they are so old and widespread in science that this paper from almost 30 years ago already contained them, and I've paraphrased those problems from exactly that paper. And all of these kind of scenarios, they are examples, real-life examples of where data management goes wrong. And it can go wrong on these small scales, affecting individual researchers, affecting individual projects, but it can also sometimes go wrong on larger scales. And there it affects entire fields, making them more inefficient or less reproducible in general. Now, solving these kinds of problems individually is not witchcraft. There are many tools, and there have been many tools, many resources, lots of knowledge on how to prevent that. The authors of this paper 30 years ago, they already knew how they could fix those problems. And I'm fairly certain, I'm actually quite sure that there are many people here in the audience who actually contribute, actively develop tools that help with many of those data management or reproducibility problems. So it's not like we don't have the tools. It's not like there is not the knowledge about how to prevent those things. It's just that they are not widespread enough. They are not frequently enough applied. And in my opinion, the very first step that is needed in order to apply a tool, apply some knowledge, is knowing about it, knowing about its existence, and then being able to, identify whether it solves the problems that you have. And this is why I'm here today, and I'm going to talk about DataLad, which can help with small or large-scale data management tasks, and is a free and open source command line tool with also a Python API. Because some people might not know about DataLad, I want to give you an idea of what the tool can do for you or what the tool does by showing you some of the real-world examples where DataLad actually is in use and where you might have seen it already without knowing it. So one way to use DataLad is to share or consume datasets via GitHub, GitLab, the Open Science Framework, the European Open Science Cloud, and many similar services. And this looks like this one. Here's a screen recording. This is a GitHub repository sharing neuroimaging dataset of about 20 subjects. And you can get a Git URL, as you have seen in the Git tutorials, and you can plug that into a clone command, not a Git clone command, but a DataLad clone command. And you can see how after a couple of seconds, this clone command has retrieved a repository. And you can take a look at the contents of these repositories here in that recording. It's the Unix ls command that lists files. And you can see how it's a bit structured dataset containing probably dozens of gigabytes of neuroimaging data. And what you can then do to consume this data is to issue a DataLad get command that on demand downloads the contents from those files, which are yet missing from the dataset. More on that later, but an alternative way to look at this kind of thing is from the perspective of the hosted providers, which DataLad is also used in. So many of the neuroimaging data portals that we are very lucky to have, for example, OpenNeuro, use DataLad or some parts of it, for example, as a backend. So OpenNeuro runs DataLad in the background for data management and data transport. And you can profit from that because you can go to an OpenNeuro and find any dataset like this one. You might have seen it in the recording. It's more than 1 terabyte in size. And OpenNeuro provides a URL for each of these datasets that you can then just as well plug into the DataLad clone command. And just as in the example before, retrieve the dataset in a couple of seconds and then browse and then retrieve the contents that you need for your project and precisely those contents that you need. Once you have a system where you can distribute data easily with, you can also use DataLad to create and share reproducible open science. So for example, by creating repositories such as this one here that do not only share the data, but for example, also the software, the code, and the digital provenance, a record of what has been done in order to create a scientific result. So this repository right here, that belongs to a paper me and a couple of colleagues wrote a while ago. It's a real paper, it has figures, it has tables, and it shares more than data, more than code. It actually, once you clone it, does not only contain the revision history where you can flexibly explore what has been done in this project, but it actually contains the complete setup to recompute itself. So if you want to reuse that paper, if you want to tweak some parameters, if you want to use it, the algorithms it reports on different data, you can go to that data set and then run a single command that Russ has used on Monday in his lecture, or mentioned, the make command. And then that paper computes itself from scratch, recomputes all results, and that's them in the paper, in the PDF, and so on. And this is an example that I like even more. This one is a supplement of a very nice paper, and I like to show it because of the variety of tools that this principle works in. What the authors did there is they shared 1.5 terabytes of their data openly, and then they created an entire bookdown project in R as a supplement for their papers. And you can see how you can browse all of the results, all of their code very nicely. And then as a final example, what we use it for in the institute where I'm from, we use it as a central data management and archival system because we are one of those institutes that uses plenty of the open neuroscientific data sets available. But as you've heard in Damien Ike's lecture, the data usage constraints of those data sets are rightfully strict for some reason, for some data sets. So as a form of access control, we have this bundle of data sets that can be retrieve with a clone command in order to browse which data is available, both original, processed, or archived. And then if I'm a researcher with access to a particular project, having signed the data usage agreement of, for example, ABCD, I am allowed, or I can issue a get command that retrieves the data. And if I wouldn't be allowed, then that get command would not provide me the data. So if I were to summarize DataLad's core features, I would say there are the following three. For one, it's joint version control, building on top of two established version control tools. And that allows you to not only version control your code, but you can version control your data and your software alongside. The next core feature is provenance capture, which allows you to create and share machine-readable, even re-executable provenance records for reproducible, transparent, and fairer research. And then the last core feature are decentral data transport mechanisms that allow you to, install and share and collaborate on data in the way that I've just sneak peeked you. You can publish data in this way. You can update your own published data. You can update from published sources. You can retrieve data file contents on demand, and importantly, in a streamlined fashion. You can also distribute files in a decentral network, importantly, on the services or infrastructures of your choice. And what I want to do in hopefully around the next 60 minutes is to give you an idea of how DataLad works and show you some of the core commands, also some of the technical features that I would want you to understand if you want to work with it. And I want to do this in a live coding way. And in order for you to follow along, I have had this page here in the DataLad handbook. If you go to handbook.datalad.org, it's also in the Slack. You can go all the way down, and then you should find this page here, NeuroHackademy 2022, Data Management for Neuroimaging with DataLad. And there's lots of text that explains most of the things that I'm doing so that you can also revisit this later. But the important pieces are these gray boxes here, the code boxes that we're going to execute. And if you hover over them, you can see this little code, copy symbol here, and you click it. And then you have it copied into a clipboard, and then you can go ahead and control V it into the terminal on the Jupyter Hub where this can be executed. What we're going to do is not only, oops, one second. So if you go to the Jupyter Hub, let me actually open up the launcher so that you can see how I got there. Sorry. So here's the launcher of the Jupyter Hub that you should all have access to. And because DataLad is a command line tool, we're going to open up a terminal here where we're going to type those commands in. And you can just copy and paste them, and I'll try to not make typos while I type them in live. Now, DataLad is a command line tool. That means you're just going to type its commands into the terminal, just like that. And the commands are made up of different parts. One part, or the first part, is the main DataLad command that always comes first. If you just run that, it will complain that it doesn't have enough information to work with you. But you can add certain things to it. You can parameterize the main command, for example, with the -- version flag. It tells you the version that is installed. Or you can add a subcommand that is a specific command that actually entails a DataLad action. So one example is the DataLad WTF command that reports plenty of information about the system that we're running on. So if I execute this, I get a couple of pages of information about, for example, the system that I'm on, and that can help me figure out certain aspects that are relevant for data management. These subcommands also have additional options and parameters that you can use to modify their behavior. For example, the WTF command has a capital S option. This is short for section, and that flag allows me to limit the output that I'm getting to a specific to a specific piece of information or several. So I can say if I'm only interested in system information, DataLad WTF dash capital S system, and then you can see that the output I get here is much smaller and only entails the system information. If you want to get help, you can always look online into our docs, but you can also get help directly from the command line, which is sometimes useful because it's just faster. If you do -H, for example, after a subcommand, you will get like small help, short help, entailing just the options with slight, very short information about the command. If you need more help, you can do -- help, like big help, and that shows you the command with a little bit more of a description. You can see the explanation for all of those parameters that it has, and oftentimes commands also have concrete examples on how you use them. And in case you're also seeing this right here, you know, this weird thing where you can't type, but you can scroll up and down with the arrow keys on your keyboard. That is called a pager, and if you're ever inside of that in a terminal, the way that you get out of there is Q. All right, let me quickly check back into my slides. So just to give you a proper intro into these kinds of prerequisites. DataLad is a command line tool. I've shown you how the main execution kind of looks like. Importantly, if you want to use it into your scripts, you can. It has a Python API because it is written in Python. And if you have another language that you want to use it in, like R, MATLAB, whatever, you can just use system calls in order to execute DataLad commands. And then, just to summarize what I've just shown you already, you have a DataLad command followed by a subcommand. Both of those parts of the DataLad command can have options that alter or refine the way that they work. Here's some examples on how that might look like. And you can get help from the command line in order to find out more about specific commands, scope, the options, what it does, examples, etc. All right, so let's start this live coding session with DataLad's core data structure. And this data structure is what we call a dataset. And you can either create datasets from scratch, you can create them by force in existing directories, or you can clone them from remote places. And in whatever way you do this, once you have obtained a dataset, it feels like a regular directory on your computer. You can see here a terminal view, and you can see a file browser view of a DataLad dataset. And it looks like a directory. It essentially is a directory, but it is a directory that is managed by DataLad. Importantly, a dataset is completely content agnostic, so you can put whatever you want inside of it, and it doesn't involve any custom data structures. If you put a PDF in there and give it to DataLad for management, it will stay a PDF. It will not be transformed into anything that is not a PDF. All right, so let's go into the terminal. I'm going to make some space here by pressing Ctrl-L and create a dataset. And for this, we're going to use the DataLad create command. This one needs one parameter, and that is the name of the dataset that you want to create. Essentially, what will happen when you run DataLad create my analysis is a new directory, my analysis, will be created on your system, and that is a directory that is a dataset management. Now I'm going to parameterize the DataLad create command a bit. That helps me explain some of the technical features of the system later. And what I'm going to parameterize it with is the -C option. This is short for configuration. And the configuration I'm providing is the text to Git configuration, which performs a specific type of configuration in the dataset that I will talk about a little later. When I execute this, you can see that there will be a little bit of output printed to your terminal. It's generally useful to read that kind of output in order to figure out what is going on, but you also have a status report in the end. Here you can see that it is summarized with the commands that were ran and whether their execution was okay. And here everything is fine, so this is good. And if we now take a look inside of that newly created directory, you can also see it here in the file browser. Then there indeed is, a new directory here. I can list its content with the ls command. And I can also take a closer look into the contents of that dataset by running ls-a. That is short for all, and it will also display hidden files. And you can see here that there are some hidden files and directories. They look similar to what you've seen in the Git repositories that you created in the intro to Git tutorial. And they hint at the fact that some version control is happening here in the background. So back to my slides. On a technical level, what a DataLad dataset is a Git annex repository. What that means in a practical way is that you can version control files regardless of their file size or type in it. And that process has two means to come into play. You can either make use of DataLad commands that I'm going to be demonstrating. Those might be beneficial or easier because they try to be less complex than corresponding Git or Git annex commands. But because this is like a fully functioning Git repository, Git annex repository, if you are a user of those tools, you can also just make use sorry, of the commands that they provide, also for subsets of the things that you do. And now let's take a look into how version control works. For this, you've already seen it kind of, or you might have guessed it, like by the name that I've given that directory. The stuff that I'm going to do here in this live coding hands-on tutorial is I'm going to create some sort of analysis, a data analysis, with a toy example, nothing fancy. To show you the commands, and I'm just going to play with that narrative of a toy analysis. And the first thing I'm going to do is I'm going to create a README file just to be kind to the people that I might share this data set later with, so that they have something to start their exploration process on. So if I run echo my example DataLad dataset, and I redirect this string into a README file, readme.md, then I have created a new file with that string as content. Note that I'm using redirection here simply because I want to work in the terminal. You can just as well just create these files with editors of your choice, however you would usually create text files. I'm just going to stay here in the terminal because it's easier for me during live coding. Now we have added a file to this DataLad dataset, and DataLad status is the command that reports on the state of the dataset. And now that there is a new file inside of it, it is reported as being untracked. And in order to save this modified state, in order to version control the file that we have added to the dataset, I can run the command that is called DataLad save, and I can attach, similar to how Git commit works, a helpful commit message that helps me build up a nicely readable dataset history that hopefully entails a nice, diary-like overview of the things that have happened in the dataset. So I highly encourage you to provide meaningful, well-made commit messages. So here, for example, I can say create a short README to describe the change I have just made. Again, we can see all of the status reports at the execution of the command, and that's it. You've version controlled that file. I can then go ahead and echo something more into that file just to show you how modifications look like. So if I say echo, this dataset contains a toy analysis to, describe a little bit of the contents of the dataset, and I'm going to append. So this is why I have these two arrows. Those those words to what is already in the README. Then I have modified that file in git diff, for example, just to also show you how git commands work just as you would expect them to work in a git repository here. Shows us, as you know from git repositories, how this kind of modification is represented in the dataset. So you can see here the addition of these lines with the green color highlight and the little plus at the start of the sentence, and DataLad status shows the file to not be untracked anymore, but the most recent change that we made of it shows up as a modified file state. And just as the untracked state, we can save this modified state with a DataLad save command that we parameterize with a helpful commit message, such as add info on dataset contents to the README, and done. And then I can also take a look at git log in order to see an overview of the revision history I've already created, and you can see how our commit messages from the past two commits, they all show up. You can see lots of things that you have seen in the sessions on Git: authors, dates, these 40-character string commit hashes that identify commits uniquely. I'm going to skip showing you how to version control a terabyte worth of files in such datasets. It's very easy. You add the data into that directory. You just copy it into it, and then you run DataLad save. That's it. You don't need to care about the size of the files because while you shouldn't do that in Git repositories, in DataLad datasets you can version control large stuff as well. But the way to go about saving this, to go about committing this, is exactly identical regardless of the file type. You can just go and do DataLad save. What I'm going to show you instead is how you can also version control some special files, because research does not only entail, code, readmes, data. It also entails the software. And the past sessions on software containers have shown you a very powerful tool, software containers, that can help you with your science, because they can encapsulate software environments for you, and DataLad datasets can take software containers and version control them alongside of your code, alongside of your data, and so forth. And while I could just take a container and put it into that directory and save it, that would be fine. And we've also added some functionality into DataLad that helps with then also making use of those containers in specialized commands that aim to help with reproducibility. So in order to add a container, I'm going to run a DataLad convenience command that performs not only saving of a command, but it performs something that we call registering a container in a command in a dataset. And when a container is registered, a later command execution can actually execute, for example, a script, for example, a command line call inside of that container. And for this, I hope I don't mistype. I run the command DataLad containers add. That command needs a name that helps me identify the container. This can be arbitrary, and I'm adding a nylon container to my dataset, so I'm calling that container nylon. And then I need to supply a URL that identifies where that container comes from. This can be a local path, but it can also be a URL. So I'm going to, in this case, provide a URL where I have deposited that container, nylon container latest. And while that executes, I'm going to talk a little bit about the type of container that I'm using here. You can see from the URL, it doesn't look like a Docker Hub URL, and that is indeed because it's not a Docker container. It's the alternative technology that you've heard mentioned, but you have not explored. That is called Singularity. And personally, I'm a Singularity user. I'm a fan of Singularity because it allows me to run software containers on high-performance compute clusters, which is definitely a problem with Docker containers because of the elevated permissions that they require. All right, if I run DataLad containers list, I can see that this command is registered here under the name that I've given. And that concludes my short detour on version control already. And so let me just summarize that and also motivate this, because you might think, why on earth would I need to version control all of it? Why on earth would I need to have such exhaustive tracking that I would want to version control not only my code, but then also my data and also my software containers? Now, the reason is that all of these things are relevant. And you know from stuff like your manuscripts, like your analysis code, that such building blocks of science are rarely ever static. They evolve over time, they change. And the same is true for data. For various reasons, you can have studies that simply have additional acquisitions added to them, so they grow in size. You can have data where you have errors that are fixed over time. And you could have also data that complies to the bit standard ones, which you should definitely do. It has plenty of advantages, more than I can than I have time to talk about here. But just because they've complied once to the bit standard does not mean they are compliant forever, because it's a community standard, so it improves over time. And in 10 years, maybe, the community standard that bits is might have improved a little bit more. So your data isn't compliant to the most recent state of bits at some point. And then you will want to rename those files. And that would be a change, an evolution in your data as well. Here, for example, is an example of erroneous data that was fixed in different versions. If you're using the ABCD data, you might have heard about this, where the post-processing of some files from certain scanner was affected by a flipped sign. And then the ABCD had this nice transparent statement where they alerted the users that they shouldn't use specific files in a specific version. And if they had used those files, that they needed to rerun their analysis and recheck their analysis. And that later part, like recheck their analysis, that is the reason why, having this kind of tracking is important, because when these building blocks change and the data changes, then because they are prerequisite for the results that we're getting, their evolution also affects the evolution of the results. And unless you have a clear idea which code was run on which data in which software, it becomes hard in hindsight for yourself and also for others who are not involved with your project to actually find out exactly what was done and where the results come from that you have computed. So when you use version control, you have kind of a prerequisite to answer these questions. And here's an example from a project. I hope this is readable. It's a little bit small, but the commit message is seeing a commit log here of a data set that says fixed typo in physiolog converter. And then the commit on top of that says re-import respiratory trace after bug fix in converter. And then I can also take a look into that commit and see the details of it, and I can see that some data has been added to that data set here. This just from the diary-like structure of the revision history lets me know the story behind this, and I can transparently find out which of the data I might be using in the analysis, where in the progress of that history I might have performed my own analysis, whether it was on the respiratory trace data that contained a bug, or whether it was on the fixed respiratory trace data. All right, so that was version control. And the next feature that I want to take a look at is digital provenance. And digital provenance, you have heard it quite a few times in these past few days in different lectures. The way that I like to define it is the tools and processes used to create a digital file, the responsible entity, and when and where the process events occurred. And you know that from just the looks of a Git commit history, some of these provenance elements, they are already included once you do version control, like the commit ID, the author, the date. However, there is some more provenance that DataLad can help to capture that is not only descriptive, but that can also be actionable and used by a computer to reduce something or to retrieve something. And I'm going to show you two examples of that. One is the, consider yourself in that scenario again, where you receive a PDF from a colleague via email, via Dropbox, via whatever, and you save that, and at some point you find it again on your computer and you just don't know where it came from. Or you come back to your project and you find a figure that you really like and you want to know which script produced it, but it is unclear which script was the one that produced that figure. And there are two commands that I want to introduce now that help with creating this kind of provenance. And for this, I'm going to clear my terminal again. I'm going to start by actually showing you, the like normal piece of process, like how you would go about retrieving stuff without provenance. And I'm actually going to copy that because that's a long URL I don't want to mistype. So you should be down here. And what I'm doing here, oops, Control B, that's it. What I'm going to do here is, let's say in this toy analysis, I'm pretending that a colleague of mine sent me a script that I can use for my analysis. That happens. And here I'm using a wget command to download it from the internet, but this might just as well, be drag and drop from email to directory, or, right-click download or something like that. Just because I'm doing such things in the terminal doesn't mean that everything has to happen in the terminal. I'm just using it because it makes my life here in front of the terminal a little bit easier. So wget downloads that file. You can see if I go into the file browser over here, the code directory now has a Python script. This is the one that I've downloaded, and DataLad status reports that directory. As expected, is untracked. It contains a new file that it hasn't seen before. And if I were to save that, I can say DataLad save, adding a nylon-based script for brain masking, and brain masking, which is what that very simple script does. And this is the standard way of doing things, which is like it already contains the version control, provenance, which is nice. But where did that file come from? I will have forgotten in 5 months. There's no track record of how I retrieved that. A different way to retrieve content from remote places, but then also internally secretly registering the location in a way that becomes useful in a couple of minutes, is by running a command that is called DataLad download URL. And that, similar to wget, essentially performs a download of web sources, but it does a little bit more. So I'm hoping I'm not messing that up with the URL. So the first thing that I'm actually going to provide DataLad download URL with is a commit message. So I say add a nylon tutorial, because going on in that narrative, I might not be very familiar with nylon, so I'm just also retrieving a tutorial that tells me how I can use the script that I have just received from my kind colleague. And I'm going to give it a output directory, output name, where I want it to end up. So I'm going to call it nylon tutorial.pdf. And now I need to provide the URL, and oh man, how I hope I do not mess that up. So this is also in GitHub, raw.github/user-content.com, that handbook resources mastermind learn tutorial.pdf. And luckily I did not mistype, and it retrieved an actual file. The very first thing that you might have noticed is that there is a save summary here in my command summary. If I run DataLad status, it kind of confirms it because the DataLad state is clean. And if I take a look into the history, let me show you the most recent commit. Here it is. There it is, already saved for my convenience. Now, internally, this command has registered some actionable provenance, but it will take me a couple of slides more. Like, I need to reach the transport phase of the lecture to show you where that provenance will be relevant. Until then, I'm going to jump ahead to the different kind of provenance I wanted to introduce, the process provenance that can capture information on processes producing output files. And for this, I'm going to, in the narrative of my toy analysis, pretend that the script I had received from my colleague does not follow exactly the type of Python formatting that I typically do. And for this, I'm just going to run a command line tool that is called BLAG. It is a Python formatter that is, it's an opinionated Python formatter. So you can give it your Python scripts, and it will reformat them to certain standards, also ensures compliance to certain standards within Python. And just to show you how that typically would work, you just say BLAG, and then you give it a Python script to operate on, and then it will go check that file and reformat it if necessary. So here you can see it has done something. It reports that one file is being reformatted. I can actually use the version control tools now to investigate the amount of this change. You can see here, it wasn't much that was reformatted, just some quotes, but for the story example, it's okay. But I actually don't want to do it like that, because this simple reformatting, it might not be something as irrelevant or as minor as reformatting. It could instead be something that might be creating a more widespread change. It could be an analysis. It could be reformatting of entire data sets to a new version of the bit standard. It could be a script that is ported from Python 2 to Python 3. There are also command line tools that do that. And I want to capture that process. So I'm going to briefly restore that change from my work tree so that it is all clear again and nothing in that dataset state is modified. I have essentially undone the modification that BLAG just did. And in order to show you, or in order to record process provenance, I'm going to essentially run the same, actually I can bring it just back. I will rerun the same command, but I'm going to wrap it inside of a command that is called DataLad run. And the only parameterization that I'm adding at this point here is a commit message where I can say DataLad run, and then I'm going to describe what I'm doing with it, reformat code with BLAG. And running this will then again, just as download URL, save me the process of saving a modification. It will save what has been done for me. And if I take a look inside of that commit that was created, you can see not only, is that represented here quite nicely, but you can also in the commit message see this weird provenance or the structured record that presumably is provenance. It's a little bit weirdly structured. That's because it's meant to be read by machines, although you can make sense of it, because you can see here in the command field of that structure that it, for example, encodes which kind of command has been run during the process that resulted in the change that you can see summarized below. Going back to my slides, DataLad run is essentially a very stupid command. It's just a wrapper, and it takes anything that you can express as a command line execution, and it will perform the execution and investigate the dataset's state after execution finished. And it will then take all of the resulting new files, all of the resulting modifications, and save them together with an optional commit message you provide, but also associates it with the command ran that it wrapped around essentially to link those, to link the command execution and the outcome in dataset state. And the nice thing that this provides us with, promised you actionable provenance, is that it can be redone by a machine if it's nicely captured. So I can say DataLad rerun. I can leave that command as is. It will go back and look if there's a run record with such a structure here close by, and then it will take it. I can also go ahead and take the commit ID of a run record that I would want to rerun. I can also specify a range and rerun many things, but here we'll stay simple and just rerun once. And then it will go ahead, take the provenance record, re-execute the command it recorded, and checks if anything has changed. And here, not all tools do that, but Black nicely tells us that in this case, because the file is already formatted, nothing has been changed. One file has been changed. But in cases where the tools don't actually tell us that they did something that changed outputs that might have already been there, we can also take a look at the revision history. So let's say here, git log in one line so that it just doesn't take up so much space on my computer. And I can see that there is a single command associated with the commit message I have given it. If there was a change that resulted from re-executing the command, I would see a second commit that versioned the changes that the rerun would have introduced. All right. And then coming to the third core feature that I wanted to introduce, data transport. And I have shown you many DataLad drone commands in the screenshots, the screen shares that I've shown you beforehand. So I trust that you get the principles, not so hard. So I will add an additional piece of information to this part of the live coding, and that is not only cloning datasets but linking datasets, or as we call it, nesting datasets. And that has several reasons, and one of them is reusability. And to motivate that, I want you to think about the typical evolution of a scientific project. In neuroscience, our projects are generally not super monolithic. It's not like we have one piece of data and then just a single process that results in a paper that we can publish. The data that we have that is acquired in a very time-consuming step, and then you typically add some pre-processing, maybe some conversions to specific file formats, to community standards, etc. to that, and only then are you able to, based on pre-processed results, perform some analysis, or then some smaller grained pre-processing. So the process from raw data to paper is quite multi-step, and the best way to go about this kind of multi-step process would be to keep all of the stages of that process as easily reusable as possible. And the way that we advocate for this in DataLad is by advocating for modularity, where we advise that whenever something is a standalone unit that can be reused in more than a single context, for example, pre-processed data can be reused for several analyses, that it stays a modular unit in the form of a single data set. And instead of adding other parts of the evolutionary process to a data set, we advise to simply link those as dataset dependencies. And this is performed via something that we call dataset nesting, but you can think about it as a sort of dependency declaration, where one dataset declares to be dependent on a subdataset or several subdatasets that it contains. And I'm going to show you how that looks like. Let me clear my screen. Whoops. And I think I accidentally, now you should be able to see the text. Okay, so the way that I'm going to continue here with this toy analysis is I need to have some data that I'm acting on, that I'm running my analysis on. And I want to keep things modular, so I'm not adding the data directly into that dataset. I'm linking a published dataset in a precise version in order to operate on it. And the command that lets me link datasets is also DataLad clone, but it gets the -d, which is short for --dataset parameter, pointing to the dataset that I want to link it to. And I can use the Unix concept dot, referring to the current directory, to say, clone me something into the current dataset and link it to it. And what this command needs is a URL. I'm going to hopefully not mistype it, https din.genode.org/my username and then the dataset I want. I hope that I didn't mistype. And then the final parameter or argument I'm giving to that command is where I want to have that dataset cloned under, like what name do I want to give the clone. Here I'm going to rename it from bits data to input, because that makes it easier for people outside of neuroscience to know that this is, the data that I use as input. Bits data sometimes might not be as clear. So running this, we'll go to Gin, which is essentially a different form of GitHub. It's a Git repository hosting service, very, very useful. It will go and clone that and register it as a dataset called input in my dataset. I can run DataLad subdatasets to see this. Here it is. And I can list its contents. And here you can see that it's a bits formatted directory with not many files, just a single subject. But hey, we have something that we run our analysis on. Here you can also see it in the file browser, a little bit nicer rendered than the terminal does it. And if I take a look into the commit that has been created about this, you can see that this looks different from typical commits you've seen. There is a little bit of what I could call provenance. It contains, a path to where that dataset is inside of the dataset. It contains the URL it came from. It also contains a unique ID, and it contains something very important, which is the subproject commit. And this subproject commit is a commit hash that identifies the state of the dataset precisely. And this is what allows me to later be able to uniquely, transparently, completely identify which version of the data I have run my analysis on, because it is linked here as a precisely identified version state. So back to the slides. Here is what nesting looks like. You have data when you clone datasets inside of other datasets, you create what we call a super dataset subdataset hierarchy, and the super dataset registers only some parts of the dataset information, of the subdataset information. It does not, include the revision history of that dataset. It includes, however, information on where the dataset can be reobtained from, where does it come from, and it contains information on which version of that dataset was installed. And that is also actionable and can later be used to redo something. And to then go back to something that you have seen in the screen recordings I've shown you, because that cloning was so fast, even though it's just a single subject, it's impossible to have that subject's data already be downloaded on the cluster that we're running this on the Jupyter Hub. And you've seen that I can issue a DataLad get command. Here I'm doing it across dataset borders. That's something that's very useful to see. I'm just going to specify the directory as is. It will retrieve all of the contents. I can DataLad get those file contents on demand using the DataLad get command. And here you can actually see how a download is being issued that retrieves me this file on demand. I'll go back to my slides while this is done, because this is something that is very unique to a Git repository, in case you've only dealt with Git repositories now, but it has immediate advantages. So when you clone a dataset, it is very lean. It contains what we would simplify as metadata, namely file names, availability, but it doesn't contain file content. So when you take a look at the size of a dataset after we've cloned it, it's just a fraction of the size of the data that it usually tracks, especially for those large neuroscientific datasets. So you can go and browse the files, the available files in the dataset without needing to store them necessarily. And if you need a particular file or set of files, you can just get them on demand, like I've shown here. And the immediate advantage of that is that you have access to more data on your computer than you actually have disk space for. So you can easily have the entire Human Connectome project dataset readily available at your fingertips at a fraction of the disk space size it would typically contain, and you can get those files on demand. Now, this one is still downloading, so I'm just going to continue with the slides. And instead of starting with the command line call, I'm going to start with the slide on the next thing, because what you can also do, you can not only get the file content on demand, you can also drop the file content that is not needed anymore by running a DataLad drop command, and that will keep you you will keep the access to the file. You will keep the file name that you can browse, and you can rerun a get on it to retrieve file content, but it will free your dataset from the dataset contents. And that opens up the door for like disk space aware analysis for datasets that are really large, where you can retrieve files on demand once you are computing on them, and remove or drop the output once you're done with it, and then only remove the input once you're done with it, and only keep the output. And sometimes you may not even need to keep the output because you, for example, have a provenance record that tells you exactly how it can be recomputed, for example. So here, the download has finally finished. I will quickly show you how a DataLad drop looks like. So DataLad drop input, blah, blah. I'm just going to provide a little bit of the path. It will just drop everything it finds underneath there. You can see how this has freed up the disk space again, or at least it said drop, and I can assure you that it freed up some disk space again. Now, this is peculiar behavior, and understanding that behavior is very crucial to understanding how datasets work and working productively and confidently with them. And explaining why that is the case brings us to the question of why are there being two version control tools? Why do we have Git and Git Annex? And the reason for this is that Git is not alone capable of version control in large files. I'm just trying to explain in simple terms why that is the case. So when you have a Git repository, what Git allows you to do is to check out past states of files. And when you do such a Git checkout of the past state, your repository view is that of the repository at that state. And so Git needs to be able to present you with the state of the files as they have been in the past for each of the commits that you make. And here's a little figure that illustrates that a little bit. So let's say you have 3 files in version 1 of your dataset, but then you make one commit that catapults your Git repository into the second state. And Git needs to then, internally represent this somehow. If you have a file like file B that doesn't change, that is not affected in the commit, what Git does is it creates a pointer that just points to the first version of that file. That is a very space efficient way of, of handling it. If you have a file that evolves in the second state, like file A1, what Git needs to do is it needs to represent both that state A1 and the state of A in the repository. And because Git has been made to work with text files, if file A1 is a text file, then Git has very efficient ways that allow Git to, not simply keep a copy, a second copy of that file, but it can represent the difference, the exact difference that is much smaller than a copy between those files, and store it very efficiently internally. The problem comes when you add large binary files. For example, you have a 5 GB brain image, and that is a part of your dataset at version 1. Now in version 2, so the first commit you make, you change a tiny piece of that data. You take a look into the header, you find a misspelled first name and you fix it. And what happens next? The thing is, because this is a binary file, Git doesn't have very efficient strategies to representing the difference between the first state and the second state of the file, even though the absolute difference, like the absolute change, is just a couple of bytes. But Git doesn't know how to represent this. Git doesn't know about the nature of this change at all. So the only thing it can try to do is to actually create a complete copy of that large file. And with that, you add another 5 GB to your repository. So at version state 2, your repository also already is 10 GB large. And if you do that too often, you can break a Git repository. It takes a while. Git is a very powerful tool, but you will bring it to its knees if you do too much of that. Sorry. This will primarily affect performance within Git repositories, and even more so, it will affect performance when cloning, because all of that data that is included in the revision history, that needs to be transported when you do a clone. So when you do a Git clone of a large repository version controlling huge files, then you have to download all of that, and then it will take ages. So that is inconvenient. But on practical terms, the more severe impact comes from Git repository hosting services that we all love, because those put a cap on the number, on the amount of file size that they allow. So if you happen to have a large file, I think for GitHub it's currently 50 megabytes, added, committed in your history in a Git repository, Git will refuse to accept a push. And that is terrifying. That is a very bad situation, because it involves very destructive actions in order to get that large file out of your revision history again. So version controlling large files is a very bad idea on all of these levels. So Git Annex, the other version control tool, is actually the tool that saves us here. And let us take a look at how this works. What Git Annex does is it adds version control for large files without needing to check that large file's contents into Git, but nevertheless making use of Git's phenomenal version control capabilities. And a dataset, a DataLad dataset, has two parts. It has a Git part and it has a Git Annex part. And we try to put all of the large files, all of the binary files, also private files, into the Git Annex part of your dataset, where they can be version controlled without ruining your Git repository. And to just take a look into some of the technical details of this, here is a look into how Annex data, or how Git Annex stores large data. What you're looking at here, and this is the output of list command of the file in your dataset. You can also run this, but you should make sure to retrieve that file again to see that. Best is that what seems to be a normal file is actually a pointer. On this type of file system, it's a symlink, a symbolic link similar to a shortcut on Windows, that points to an internal place in the dataset that involves this kind of very cryptic file name. And this cryptic file name, this is the insight in the technical reason why we can version control files without checking their content into Git, because that cryptic file name contains the entire content identity of that file. And the way that this is done is when you have a file, you use a command like md5sum, a hash function that is capable of encoding the identity of a file in a character string that uniquely identifies this content. So if you have two files with exactly the same content, the md5sums, these cryptic things, they will be identical. And instead of putting the file contents into Git, we move the file contents, or GitNX moves the file contents into this internal place and renames them under a name that encodes the file content identity. And that allows us to represent file content in the revision control system as something that is just a fraction, like very few bytes of data, while internally the large data is stored in what we call the annex of the dataset, and their data transport mechanisms can ensure that it is transported to all of the places you may want to back up or save your data. If you take a look into one of the commits that include annex data, you can also see this because what is reported to be recorded is this cryptic file name, this identity encoding file name, instead of the actual file content. And what then, because just not version controlling things in Git does not, help with distribution. What is then added to that feature, or this kind of process, is the ability to transport the file contents via almost all standard infrastructure, from Google Drive to Dropbox to repository hosting services with Annex support, the Open Science framework. And internally, we keep a provenance record of all of the locations where file content is available, so that a file can be retrieved from, if need be, several different locations and distributed over this decentral network. So for this, I can actually go back into my terminal and run it here. If I run git annex where is, whoops, I missed a command, git annex where is, on the file that we added with provenance into the dataset, the NeuroHackademy tutorial, git annex reports several locations that are available. The my analysis dataset here on the system, and then also a special place, and here is the URL that we actually retrieved it from. And what that allows me to do is I can DataLad drop that NeuroHackademy tutorial, and then I can re-obtain it really flexibly. Ta-da! All right. So there are two practical consequences of storing content in Git in Git Annex versus in Git, and I want to make sure that you know about them so that you have an idea when you're actually working with DataLad datasets. One of the practical implications is that Annex contents are not available right after cloning. A explicit get retrieves them from wherever the file content is stored and being made available to you. You already experienced that. A different practical consequence is that files that are stored in Git Annex are protected from accidental modifications, because it would kind of destroy the association between file name, content identity that we have made. I'm going to show you how that is handled with. But these practical consequences make the different tools differentially suited to version control different forms of data. Git handles small files well that are also frequently modified. It's essential for code, for like text files, something like that, and also for files that you want to have available right after someone has cloned your data set, like a data usage agreement, for example. Git annex, on the other hand, should be used for files that are large and binary, and then also is a very good place to store files that you want to keep private, because they are not exposed right away. At least their contents are not exposed right away when you get a clone of that data set. And you, as someone who controls the data, can very flexibly make sure that file contents are only available to certain persons, or not at all, so that a Git actually does not need to retrieve data that you version control for all people that you share your data set. All right, and so having outlined the differential advantages of these two tools, it's also important to learn how you can influence where your contents are stored. One of the ways we've already experienced are configurations that make your dataset put files into Git versus Git annex. One of them is the text to Git configuration that will put everything that is a text file into Git. You can also make rules, such as all of the files with a given extension, all files that are smaller than a given size, all files in some directory, all files that match a given file pattern. And then you can also do it on a per command basis, for example, by just using Git command, but also by doing DataLad save with a to-Git flag. All right, and now the final thing that I want to show you is I want to take provenance capture to the next level and extend it to computational provenance. I can't do that on the Jupyter Hub, so I'm going to do something else instead, but I'm going to show you the computational provenance. Because now we have lots of building blocks inside of our data set. We have data, we have code, and we have a software container, and we would be stupid not to use that to, in a provenance tracked manner, analyze our data. I'm going to show you how the script that I ran would be executed. It's a Python script, so I would say Python code get brainmask.py. And this is the command that I would run. And obviously, I'm going to wrap it. I'm going to wrap it again in the DataLad run command. I'm going to include the software provenance on a system that can actually execute containers, because this system here is running in a container. It's quite hard to make it execute a container inside of it, so I can't do it, unfortunately, but I will show you. And I'm going to use this opportunity, however, to show you how you can parameterize DataLad run in order to do useful things with the annexed contents of your analysis or of your data set. So I'm going to add an input flag, and the input flag is useful because it will take care of retrieving file contents that you need to get before computation can work. So I can say retrieve me input subject to blah blah. Before that, I'm going to put that into quotes, and then it will issue a get command prior to executing the Python command. And then I'm also going to put an output flag. Let me quickly type that. I know, because I wrote that script, what is going to be created as an output. So I'm cheating a little bit here. You can always just specify complete directories, for example. What the output flag does is more important for the recomputation of a command via DataLad rerun, because I told you that something that is kept in Git annex is prevented from accidental modifications. But by supplying something as output of a command, you're telling the version control tools to essentially prepare for modifications. Here, in technical terms, we unlock them, and then modifications can be written to those files, and they can be updated. So running this, data, I need to obviously also supply a commit message. So I forgot that. DataLad run, compute a brain mask, will retrieve the input data and will execute the command that I'm running, that will execute the script on the data. Now, in the meantime, while this runs, I'm actually going to show you the containerized alternative on my own system, where I have set this up as well, my analysis. And I'm going to go not with DataLad run, but with a command that's called DataLad containers run. It's almost identically parameterized. The only thing that it adds is a specification of the container that we want to use. And the crucial difference is that the execution will then not happen in the environment I'm currently in, but it will happen inside of the software container. Oops, I need to enable my environment. So DataLad containers run, it will retrieve the inputs, it will retrieve the container, and it will have created a run record that also includes computational provenance as additional information that I can rerun. And then I can go ahead and publish this. If I wanted to, I can say DataLad create sibling GitHub in order to, for example, publish to GitHub. But I would refer you to a handbook chapter on that and quickly move back to the slides to finish up my talk. So DataLad containers run is for computationally reproducible data analysis. And then when you want to share data sets, you have a wide variety of repository hosting services, third-party storage providers that you can use in order to share your data sets so that data becomes easily accessible. And what DataLad tries to do with that is it tries to provide a streamlined layer that connects the data sharing practices that people use all of the time. You have means to share your data sets successfully, but you can streamline it with a connective layer that allows you to clone, to get, and also to push, to update data sets with the services that you might already use. And that is important because you might really love those services, but some of the services that we are very familiar with, like GitHub, they can be taken away from us at some point. So they can be, because they are commercial, GitHub can suddenly start, for example, charging. And when you're not willing or able to pay for that service that you have relied on all your career, might not be feasible for you to use anymore. And the way to protect yourself from something like that, from being ripped of a service that you relied on, is by having standalone portable structures, DataLad datasets that not only can live on GitHub, but that you can flexibly also distribute to the next service that you're going to exploit. And with this kind of decentralized network, you can create a more resilient infrastructure for your data that enables you to move flexibly across services, and that makes your data safer in the long run and less reliant on centralized services. And then we can obviously also extend the session to collaboration. I don't have time for this, sadly, but with data analysis being a part of the stuff that you can put into version control, into repository hosting services, you can start to collaborate on data analysis, and then team science becomes more than code. And you can go and fix data sets that if you find errors in them, and so forth. So to just sum the main pieces of DataLad up in a couple of slides. DataLad provides the means to exhaustively track all research components. And when you have like well-structured data sets with community standards, for example, BITS, and then also portable computational environments and how they evolve over time with their revision history, you have a really good precondition to identify all of the parts that are involved in a scientific project and to reproduce it. Based on that, you can start to capture computational provenance. You can find out which data at which version was used to create what kind of output in which computational outcome. And because you have this computational provenance, your data set becomes a portable structure that you can put to different services that you can distribute with the provenance records to have a really comprehensive portable structure that captures all parts of your science. And once you have achieved that, third parties, other researchers, reviewer too, can retrieve your data sets and verify the things that you have done. And this trust is what makes reusability. So someone coming and taking your work and extending it and building up on it, safe and easy endeavor. And with that, you have the core principles, the core features of DataLad mapped to very useful, applicable, actionable data management practices. I did want to talk about big data sets, and I feel that I've run out of time to do that. But there is a paper that we wrote about a very large project where I wanted to illustrate how this how this functionality scales. Because the data sets that we're dealing with in neuroscience, they become larger and larger. They also become larger than our computational infrastructure can handle. For example, the UK Biobank dataset, which is too large for many computational clusters to store. And we have, out of the necessity to process this dataset in a way that aids this reusability, that has this kind of verification abilities, where people can come and confirm that a computation results in the data that they see right here, so that they feel trust to work with it. We have created a framework that would make those kinds of challenges also possible. And I will just simply direct you to that paper right now. I hope that it has some exhaustive explanations of what we did, and I'm happy to provide a breakout session, the next week during the hackathon, to hopefully be able to tell you a little bit about how we did that. Other than that, I have some take-home messages. For one, data deserves version control because it evolves just like code. Science relies on good data management, especially big data. And DataLad can help with some things that you might encounter in your day-to-day work. If you want to be extra nice to the computational cluster, the Jupyter Hub that we run on, then I would encourage you to clean up after yourself. I've included the commands to remove the datasets in the slides and also in the code along course. And if you want to use DataLad and have some questions, then there are many resources where you can reach out for help. We run a weekly Zoom office hour where you can discuss data management use cases. If you're sharing, if you want to publish data, you can come and talk to us. You can create issues. And there's plenty of educational material available. We have a YouTube channel where we publish all of our workshops. We have the DataLad handbook that includes lots of contents targeting research data management novices. You don't need to know what a terminal is when you get started with it. And we also have a research data management course online that where you can practice some of the principles I have introduced here. So with that, I really want to thank you for your attention. I'm sorry I couldn't make it in time. Yeah, thanks so much for your interest.